All right, so let's take a look at section 6.4 where we actually start taking advantage of the things that we talked about in 6.3. Okay,
Okay,
so in
so
this
in this
section,
section,
we're
we're
covering what's
covering
called
what's
the
called the
central
central.
limit theorem. Okay, and basically it just says we can use uh, the normal distribution for some of the most common things we do in statistical analysis, and that is we are very interested in figuring out what probabilities and proportions of of uh, exist for getting certain means, certain averages, or certain proportions. Okay, so if you remember the kinds of questions we asked in section 6.2, what's the probability that a man is taller than 73 inches, or between 64 and 69.6 inches, right? We were able to answer those questions by finding areas under the curve. We're going to ask those same kinds of questions, but about means. What's the probability that if I have a sample of 100 men, that their average height will be between 60 and 63 inches? Okay, so it's the same kind of thing. And thanks to the central limit theorem, we can answer that question because means are normally distributed. So we will do virtually the same thing we did before. So that's good. So basically, here's the official central limit theorem for all samples of the same size within greater than 30. The sampling distribution of x bar of the mean can be approximated by a normal distribution with a mean of mu, in other words, the population mean, and with a standard deviation of square root of n, or rather, the standard deviation of the population over n. So those become those become the statistics that we need, or the key data points we need for working with standard deviations and or working with questions about probabilities and proportions of or percentages of means. Okay. So here's the deal. Suppose we're working with a population. So this is the population, just the population, and that population has a mean of mu and a standard deviation of sigma. Okay, so those are just from the population of men's heights, or the population of IQs. We're going to take simple random samples, all of size n. We're going to select them. It was kind of like we did in 6.4. We've got a population of numbers, and we're going to choose random samples of size, then we did size 2. But here we got to be above size 30. Okay. The population, in order for this to happen, the population has a normal distribution, or, now that's a key word, or we're taking samples of size at least 30. And we don't need a normal distribution. We saw this in some of those videos that I created. Even if the distribution is uniform or skewed or just any kind of wonky distribution, if your sample size is greater than 30, then you can use the central limit theorem. Now here's what we know, because all of these questions we're asking are about the mean. Okay, so they're about the mean. So what we want to know is this. What's the mean of the means? Well, the mean of the means will be just the mean of the population. Okay? The mean of the means is just the mean of the population. And the standard deviation of the means is just the standard deviation of the population over square root of n. And so we need z-scores in order to be able to find areas. There's our z-score formula. It looks almost exactly like the z-score formula we had before, but on the bottom here we're using this formula because this is the standard deviation for when we're asking questions about means. All right? And we'll see an example here in a second. Now, if the original population is not normally distributed and n is less than or equal to 30, then the distribution of the means cannot be approximated by a normal distribution. So we don't get to use the normal distribution, and we don't get to use these methods. All right, so check those requirements. See whether it's normal or whether you're dealing with sample size of 30 or more. And then you got to ask yourself, are you selecting an individual value, one value, or are you finding the mean from a sample in order to do these problems? Because what we did in section 6.2 was working with individual values. So that's what we got now. But in 6.4, we're going to be working with samples and the mean from those samples. So the reason we make a distinction here that you've got to identify at the beginning is because you use almost the same approaches. All right? Which is good because you've already learned this, but you got to figure out which approach you use. The only thing that will be different is the z-score. This z-score right here is for individual values. You can see that. All right? Just like we used. That's 6.2. All right? Now, if we're working with the mean of a sample, so in other words, we're not selecting one man and finding out the probability that his height is in a certain range, but we're selecting a sample of men, and finding the probability that their average height, then this is the z-score. So those two different, make a note that those are the two differences. Other than that, the problems are going to proceed the same way. All right. So we've already mentioned these things. If we're dealing with these samples of size n, and we're then the mean of the means is right here. So we want to make sure that we understand that. And the cool thing about the mean of the means being this is it's just the mean of the population. The standard deviation of the mean is sigma over square root of n. Now this is important. The standard deviation of the mean is called the standard error of the mean, or just the standard error, SEM. Okay, so sometimes we'll call it the standard error. That's this. Okay, but it's basically the same thing. It's the standard deviation of all the means. Okay, so let's look at an example. Now this is interesting. So the elevator car in a car rental building at the San Francisco airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. This converts to a mean passenger weight of 148. So if you have, basically what they're saying is, if you've got 4,000 pounds, you're allowed 4,000 pounds and 27 passengers, then 4,000 divided by 27, right? 4,000 divided by 27 works out to about 148 pounds per person. Okay, approximately 148. So the average weight needs to be 148. All right, and that's the most you can have. 27 people with an average weight of 148 pounds. Let's assume the worst case scenario, and that is that we fill it with 27 adult males. Now we're safe as long as the average of those 27 is 148. But if the average is more, then that means we've exceeded the 4,000 pound weight limit. Assume that adult males have heights or have weights that are normally distributed with a mean of 189 and a standard deviation of 39. So this is the mean of the population, that's mu, and this is sigma of the population. Okay, so find the probability that one randomly selected adult male has a weight of greater than 148. So this is 6.2. That's the kind of question you would ask in 6.2, and we'll work on that here in a second. Find the probability, and then find the probability that a sample of 27 has a mean greater than 148. Okay, so notice the difference. In this first problem, we're saying, what's the probability that one person has a weight greater than 148? And then in the second one, we're asking, what's the probability that a sample of 27 has a mean weight greater than 148? Okay, so part A we can answer using 6.2 methods. Okay, So here's how it looks. Remember, we did this in part A. We would say, okay, and I'm gonna pencil over this. So we draw our normal curve, right down here, and say this is the distribution for men, with a mean of 189, standard deviation of 39, and our cutoff is 148. Remember, we're answering question 8 or A here. So that's our cutoff. What's the probability that one person has a weight greater than 148? So we are interested in finding the area to the right of our cutoff, right? We've done that. So what do we do? We find the z-score of our cutoff. And that's what happens right up here, right? There's our z-score formula, 148 minus the average over 39. So our z-score is negative 1.05. So this has a z-score, oops, let's not do that one. Let's use this one. This has a z-score of negative 1.05, okay? So we can then use our table to figure out what the area is. And if we look up on our table, we'll find the area to the left. So I'll pencil this in, right? The area to the left is 0.14689. So that means the area to the right, this area that we want, is 0.8531. So there is, if you take one person at random, there is an 85% chance that they will weigh more than 148, right? Which is not good, because remember, that elevator crashes if we have 27 people who average more than 148. And we're just finding that there's a good chance that one single man will weigh greater than 148. Okay? So solution A, bam, there it is. I guess we did all that, right? So the green shaded area is 0.8531. Now let's do B. Okay? Now, we can use the normal distribution if the original population is normally distributed or n is greater than 30. Our sample size is 27, so we're not greater than 30, but the original population is normal, right? Weights are normally distributed, okay? So we get to use that. Now, here's what we know about the distribution of these sample means of size 27. That, number one, their mean, the mean of the means, is going to be just 189. That's the same as the mean of the population. Bam. The standard deviation, or the standard error we're going to use, is sigma over square root of 27, so 7.51, right? Once you have that, you're ready to draw your curve. There it is. Now you'll notice they really drew it tall and skinny, which is in fact the way it is, because distributions of sample means are narrower, okay? But we're fine to just draw a regular good old-fashioned. We just need it for visual, right? Just draw a regular old-fashioned curve. We know the mean is 189. Oops, that's the mean of the means. And we know the standard error is 7.51, right? And we want to know what's the probability that if I take a sample of size 21, their average is greater than 148. So the same thing happens. I have a cutoff at 148. I want the population. I want to know the area under the curve to the right of that. And I can do it. I do it the same way. I'm just going to use a slightly different z-score formula because this is a question about sample means, and you'll see that. There's our z-score formula, right? So the z-score is negative 5.46, right? So I would label this as z equals negative 5.46, and that's what I look up in my table, and I notice that from my table, the area here is 0 plus. So that basically makes this 0.9999. There's a 99.99% chance that the average weight of this group of 27 men is greater than 148. That's bad news, right? Because if it's greater than 148, the elevator can't handle it, right? So if we work through here, you can see those numbers displayed here. Okay, so the interpretation is there's an 85% chance that a single man weighs more than 148. And there's a 99.99% probability that the average of 27 randomly select males would be greater than 148. So you can see that we used basically, so given the safe capacity is 4,000 pounds, it's almost certain that it will be overweight if it's filled with 27 men. Okay. All right. And so that's how this proceeds. All right. So I'm going to go ahead and stop there. And then I'll come back and finish the second half of this here in a moment. But you can see that that method that we used in 6.4 is virtually the same as we used in 6.2. All right. So what this allows us to do is to do some hypothesis testing, or what we call hypothesis testing. Basically what happens is if we find what we're finding when we find these areas is actually the probability of getting a certain result. And it turns out, like we've said several times in this course, is if the probability of getting the result we got is very small, then we can assume that that shouldn't happen. And so probably what has happened is instead of us getting this really once-in-a-lifetime result, we conclude that the assumptions we started with were often not correct. And most of the time, those assumptions that we start with have to do with what the population mean is to begin with. So let me show you an example here. Assume that the population human body has a mean of 98.6, as is commonly believed. Also assume that the standard deviation of that temperature is 0.62, and we're dealing with samples of size 106, and we randomly select that many people, and so the question is, find the probability of getting a mean of 98.2 or lower. All right? So essentially this is the same kind of deal that we talked about, right? The picture would look like this. There's our distribution for sample means. The mean of the means is going to be the mean of the population, which is 98.6. And then the standard deviation of the means, let me put it out there. I'll squeeze it in over here. Standard deviation of the means, or the standard error, is the standard deviation of the population divided by square root of 106, right? So there's our setup. And we want to know what's the probability of getting a mean of 98.2 or lower. So 98.2 is going to be somewhere in here. And lower is going to require us to shade this area to the left. And so the question is, the answer to the question is whatever that area is. The probability of getting a mean of 98.2 or lower is that area. So I just need to find that area. All right, so let's proceed. We'll show the work that they've done here. There's the mean and the standard error, like we said, the 0.62 divided by square root of 106. There it is. All right. And we've got our picture now. They've got their bar right here, right? You can see their bar. It's way down here in the end. Doesn't really matter. The area that they've got is still shaded to the left of it. And so we find the z-score of that point, right? And I don't see, yeah, there's the z-score, right? So you find the z-score of your boundary, so 98.2 minus 98.6 divided by 0.0602 equals negative 6.64. We look that up in the table. We're going to get 0 plus, or 0.0001 is what they're calling it. All right. So that area. So the probability of getting 98.2 or less is that much. All right? So that's why we found that area, because now we can assign a probability of getting less than 98.2 or less. Okay? So here's the deal. If the mean body temperature is truly 98.6, then there's an extremely small probability of getting a sample mean from a sample of 106 subjects of 98.2. So it turns out that the researchers did obtain such a sample mean. And after confirming the sound was result, there are two reasons to explain it. Okay, either the population mean really is 98.6 and their sample just represented a very rare extreme case. Okay, that's one thing. Or the population mean is actually lower than they claimed, and so their sample, and that means their sample is more typical. All right. Because the probability is so low, it's more reasonable to conclude that the population mean is lower. It's just really probably not likely that they happen to just get that rare extreme case. So that means pro, uh, part two is probably, or conclusion two is probably the result. That is that the population that they were working with, the mean is actually lower than 98.6. Okay. In reality, it appears that the mean is closer to 98.2. So see, that's what we're able to do. Because we're able to find the probability of getting a mean that has a certain value, we can um, now answer these kinds of questions. All right. Now we've got this little blurb here. We don't use this very often, but if it so happens that we are using a really large sample size that's greater than 5% of the population, then we just multiply the standard deviation by this square root value we've got here. Okay. I don't expect that you see that very much, but there it is in case you need it.